Today's talk is about the fallacies of distributed computing. And I apologize for this horrible pun. This was my only chance to get accepted at this wonderful conference. So ignore it. It's really computing, in case you wondered. A bit about myself. So this is the slide. Believe me, I know what I'm talking about. I've been working on distributed systems in one or other form about the last 20 years. I've been doing stuff in C++, Java, Python, and for my sins also JavaScript. And in the last 2 years, focused on Go. So I consider myself as a kind of youngling in Go. I've been doing web data and big data stuff in research and at MapR, and in the container orchestration space, Mesosphere, and now Red Hat. And on the spectrum of devs to ops, I'm more on the dev side, but I'm super interested in ops topics. The agenda. So what are we going to talk about? First, I'm going to tell you what is in scope and what is not, so you have a chance to leave the room right after this. Then we're going to talk about the fallacies, about the 8 fallacies of distributed computing and how you can or might be able to address them using Go. And last but not least, we wrap up with a few conclusions. The scope. So in scope for this talk are, in general, Go programs that run on 2 or more machines. I don't really care if that's a virtual machine, a container, hardware, whatever, I don't care. It's at least 2 machines. Typically using stuff from the net package, or standard library. Typically need to coordinate to achieve something. Or I don't really care if it's centralized or decentralized controls. In general, we're talking about distributed systems at large. And this is one way to visualize that. So you might know examples from each of these categories, and if you want to learn more, there's the source at the bottom. So I've got 71 slides in 45 minutes, so I'm probably gonna rush through a few of them. But out of scope for this talk are all these things. We had a wonderful keynote in the morning talking about the channels, and there are many, many more things, and really what I want you to do is check out that book. Catherine here has you covered, awesome, and that does everything that I'm not going to talk about. What I'm going to talk about is the fallacies of distributed computing. Who of you know, oh no, let's make it less embarrassing. Who of you has heard about the fallacies of distributed computing? Raise your hands. All right. So, yeah, that's a limitation of the present tool. Yep, there we go. Before we get into that, a very quick side note. What I like to, the term I borrowed from architecture, form follows function. And that is the choice of the programming language certainly has an impact on the characteristics of the system you're building. This is kind of like, oh, really? But if you look at things, for example, I've experienced it myself at MapR, HDFS and HBase written in Java, and you've got garbage collection, and the deals have been won because of the fact that MapRFS has, or is written in C++, and doesn't suffer from that problem. There are other problems, as you know, if you have to manage the memory yourself, but this has certainly a certain impact. Another example is Kafka versus RabbitMQ, and obviously we all know Erlang is really beautiful and strong language. At least in my experience, does not necessarily outperform Kafka, which is written in Scala and Java. And last but not least, and we get into that later on, etcd versus Zookeeper. Whoever had fun using Zookeeper in production? All right, cool. Let's have a beer later on and talk about that. Right, and now we get to the fallacies. In a nutshell, all you have to take away from this talk is it's not DNS. No way it's DNS. It was DNS. A slightly more formal introduction to the distributed fallacies of distributed computing, coined by Peter Deutsch around '94 when he was at Sun Microsystems. Number 1, the network is reliable. Number 2, latency is 0. Number 3, the bandwidth is infinite. Number 4, the network is secure. Number 5, the topology doesn't change. Number 6, there is only one administrator. Number 7, Transport costs 0. And number 8, the network is homogeneous. Yeah. A little piece of advice here, brought to you by Kalashnikitty. If you now think that, yeah, sure, but it's 2017, right? It's like, come on. Like, believe me, this stuff will bite you sooner or later. And I hope that at the end of the talk, I've convinced you that this is really the case. So number 1, the network is reliable. In general, there are a number of patterns, a number of things that you can use, things like timeouts, error handling, retry logic. Specifically for Go, there are a few packages and functions within the standard library in time, in net, and context. And maybe you've already seen context with timeout or net op error, syscall error number. So these are things that you should know and you should know how to use when writing distributed systems. And there are also some really interesting things beyond the standard library, the WebSocket and the Gorilla multiplexer. And all of that, if you look at the bottom, there are, for each of these fallacies, a customized Gopher. Kudos to Ashley, whose service I've used here to create these wonderful little Gophers. Number 2, latency is 0. In general, things like cancellation, dealing with partial results, that's the patterns there. In the Go language, things like context with cancel. If you think about encoding JSON decoder, rather than trying to swallow a huge blob, a huge JSON, try to stream it, right? To take it in as it comes. Beyond the standard library, there is, for example, in X, there is nettrace that you might want to have a look at for tracing. Number 3, the bandwidth is infinite. In general, obviously, you know about content delivery networks, so being very close to your customers. Maybe at some point in time, I'm not saying you need to start with it, but at some point in time, you might want to stop using JSON and switch over to protocol buffers. I see someone laughing here. I'm not entirely sure. I'm glad that you're laughing. But, so there is that one package provided by Google, which is Golang protobuf. And I'm very, very open if anyone has anything to add here. I'm trying to put together a little website that kind of references all these things. Number 4, the network is secure. Obviously, use TLS, use digital signatures, use checksums, and there is huge. That's one of the things why I love Go so much. It has a really kick-ass, pardon my French, it has a really great standard library. And crypto being one of these packages, like, show me any other programming language that has that. But there's even more beyond the standard library. Things like crypto SSH, and for example, there are others there for all of the JSON Web Token. I keep forgetting that, JWT. You might want to look at. Number 5, topology doesn't change. So this is all about the challenges that you have if you're using a too low abstraction, for example, IP addresses versus FQDNs. And, well, that already gives it away. Use DNS rather than IP addresses. Time to live, for example. And one of the things that at least me, I ran into that, and I've seen it in other places as well. Go has a certain, let's put it that way, interesting way to go about DNS resolving. And this article, or part of this article, a blog post, essentially explains it, and once you're aware of it, you're good, right? It's really just, if you're not, then you are not in a good place. Number 6, there's only one administrator. I think that's one of my favorites, the Gopher. In general, so you can do things like auditing. You can, and you should, probably provide access control, ideally role-based access control. That's what the cool kids do. If you can, immutability. It's probably not something like one of the strongest areas of Go, but function program. We just had Aaron here. I'm personally a big fan. I'm using it. And there's I think it's a Reddit discussion, and actually a useful one. So you want to check out this immutability discussion. There is something there. So you can do it to a certain extent. And beyond the standard library, there is, for example, Caspin has an awesome library, standalone library you can use for ACL, RBAC, ABAC, and that's pretty much it. Number 7, the transport cost is 0. In general, if you think about transport costs, very often it boils down to things like marshalling, unmarshalling. So how do you get the data that sits here in the memory over the wire to the other side? And in a standard library, encoding, another area where standard library in Go really shines, has a lot of things incredible. And one of the things I came across, and I kind of encourage you to do it, maybe you want to pprof your marshalling or unmarshalling process there. And if you're ready, if you can leave JSON behind, you want to really check out gRPC. Number 8, the network is homogeneous. In general, this is a little bit related to the kind of interoperability we're trying to achieve on all levels. In my opinion, Go really has a very broad and deep and well-tested standard library across different operating systems and architectures. And there are also, beyond the standard library, things like Minio, Go, the GitHub API, and there's Prometheus, and many, many others that help you, kind of compensating for the fact that the network is not homogeneous. Now comes the fun part, the case studies. So what I did, and this was the kind of core pitch of my talk, I reviewed 5 distributed open source systems written in Go. And I won't claim that I'm expert in each of those. I know, to a certain extent, the code base of Kubernetes, a tiny little bit of etcd, and the rest is, your guess is as good as mine. To give you a bit of a feeling for the extent of the code base, I've just sorted it here for the lines of code in the respective projects. So Kubernetes around 2 million, Consul and the others around 300,000, 400,000 lines of codes. And then you see the commits and the contributors, initial commit, the releases, the stars, and what kind of vendoring they are using. So a shout out to Cockroach, folks, you're already on the right track. Okay, I see there are some other opinions in the room. That's fine. I did another step which I find quite interesting. If you look at the, obviously that's you trust only the statistics you're faking yourself, but if you look at the lines of codes per file, this is pretty consistent, right? It's not like 10 versus 1,000. You always have around 200-300 lines of codes per file, right? Interesting. Anyways, let's now jump into the first case study, which is Kubernetes. Okay, who of you does not know Kubernetes? We're going to have a word later on. All right, great. That's already awesome. Everyone knows Google initiated it. Pretty much in terms of container orchestration, the market leader. It's a bit like if you could think about a kernel of a distributed operating system. Initially, the runtime depended on Docker. That's changing now, for example, with Cryo. And there are certain things in there, like bring your own software-defined networking. And the core is actually pretty minimal, and you have to add a few plugins to make it usable. For example, the DNS plugin. The fallacies covered in the following are network is reliable, secure, and transport cost is 0. And there you see the wonderful Gophers again. So on a very high level, this is the architecture of Kubernetes. You have a control plane where you have the API server, the scheduler control manager, and they're all stateless, and the only state sits in etcd. And then you have all the worker nodes where the kubelet sits, and it's the kind of local supervisor, and everything in Kubernetes talks with the API server. Nothing goes beyond the API server. So no matter if you're using kubectl, there I said it, kubectl, or kubelet, whatever communicates all goes through the API server, and that's the part that I picked. I don't expect you to actually understand and see everything there. If you're interested in that, we've started a deep dive series around the API server. My colleague Stefan Szymanski and myself, that gives all the background here. We really only focus on this upper part here, the so-called default build handler chain. And this is a pattern that, to a certain extent, I think we heard it in the previous talk on functional programming, where you have a handler wrapper that takes a handler, adds something to it, and returns another handler. And in this case, you see a couple of things. So for example, enabling cores, dealing with panics, timeouts, having a limit on the in-flight time, if there is a request info there. Security-related things, so they essentially group it into 3 groups. Initially, it was just one chain of things. And the last one, protect, is quite interesting. And I apologize that it cuts it off here. That's the limitation of the present tool here. But I guess you can see it. It returns, this function returns both a secure and an insecure HTTP handler. And you can actually see that here in the last line, how it's done. So this is a pattern that you will see over and over again. Number 2, Consul. Consul is a lot of things for a lot of people, but quite often used for service discovery, especially if you have microservices, and can also be used and is often used as a key value store. Internally, it's using the servlib as a kind of gossiping protocol for things like communicating membership of the cluster. And in this case, it's only the one topology, it doesn't change fallacy covered. So if you look at the overview architecture, you essentially have a bunch of agents, client and server. I define that in a moment. I just wanted to give you the big picture to show you that Consul can work within one data center, whatever a data center is. That might be an availability zone or like a physical data center of yourself, and across data centers as well. I'm going to need these 3 terms, so if you pay attention now, you're having easier time reading the source code in a moment. An agent is essentially a long-running daemon on each of these members of the cluster, and can either run as a client or as a server. So it's the same code base, and then it has a kind of mode. It's either a client or a server. And then there are some other things in there, but the main point being same code base, different roles. Now, in the case of Consul, I started with some bug hunting. I reviewed a couple of issues, and I picked one that I found interesting. And this one essentially is about the behavior, the node flapping, apparently caused by some DHCP issue there. And then I followed the breadcrumb trail from the original issue through other issues, and then eventually ended up at the PR, at the pull request that apparently addressed that. So that led me to the package HashiCorp Consul agent in the file local go. If we'll have a look at that, most of the things are, okay. And I found the first one here in line 49 quite interesting. Due to some Go bug, who knows? I haven't figured it out, but okay. And then there is mutex and logger and so on. But what I really am interested in this delegate, this is what the PR essentially is all about. And then there are some other things, what you would expect, the services it tracks and the checks and so on. Metadata, channels, that's fine. But let's have a look at the delegate interface, which is defined in agent.go in HashiCorp Consul agent package. So this is an interface, and I want you to really take these 2 lines, 57 and 58, in a bit and think about it. This delegate interface defines the interface shared by both the client and the server. Interesting. I get it, why you would want to model it that way. And I'm not here to criticize the good folks of HashiCorp, obviously not. What I'm trying to figure out with these design decisions, and obviously someone designed it or decided to design it this way, is going back to Proverbs and thinking about things like maybe a smaller interface might be more appropriate, and then embedding them. I don't know. Okay, next up is etcd, and time-wise, I'm pretty good. I can take these 10 minutes Q&A. etcd, again, who does not know etcd? Okay, 2 more to my list for the beer afterwards. That's fine. etcd is essentially a distributed key value store. And for the distributed setup, it uses the Raft library or Raft algorithm, which is, I think, the claim to fame is like, this is an algorithm that is really understandable in contrast to Paxos. And the second line is actually, it's kind of like, whatever, benchmark the 10,000 writes per second. But that, if you think back of Zookeeper, and also what we're going to talk about in a moment, the change from version 2 to version 3, this is actually quite an achievement. And part of it is certainly Go. etcd exposes HTTP and gRPC interfaces, so that's really quite interesting. Has some quite interesting implications if you are operating it. And it comes with, it's fully secure on the wire, TLS with optional client certificates. And the fallacies we're going to cover are network is reliable, bandwidth is infinite, and transport cost is 0. I don't expect you to have a deep look and read everything here. Again, these slides are, by the way, online already, so 301.sh/2017-Gomputing. You can follow along yourself if you want to. The main point is essentially, if I would summarize that in a sentence, is etcd is awesome, and part of that awesomeness is Go. So I reviewed, in this case, because I was personally affected by it, one particular part, and that is the transitioning of etcd2 to etcd3. One of the changes there was this combo HTTP JSON to protocol buffers and gRPC. It's not as easy as it sounds. There are, depending on the mode and environment variables, some more combinations possible, and I'm currently actually working against the bug because of that. Then there was the change between etcd version 2, which had a hierarchical key space, so within the keys there would be a directory or hierarchy information, how keys would be ordered, and how people are using it. The good folks at Chorus essentially said, that doesn't make sense, let's make it a flat one. Which is cool, I'm totally with them. It's just, if you have been writing software against version 2 where you had the hierarchy information, now you have to change things. And if you have to support both, fun. TTL have been kind of like replaced by leases. That was the main decision around being able to survive reboots and so on. Excuse me. And then these compare and swap things have been replaced with transactions. And I blogged about it recently, some notes on this transition, kind of like here are the gotchas, and if you are on that level, maybe you want to check out this particular post. So what happened was, if we have a look at the original v2 API, that was how it was defined. So you have a context, good. You have a string, and then you have options. And you have a response object and an arrow, obviously. And you have get, set, and delete, and then a few other secondary ones. Get, set, delete. In version 3, so this one is keys API interface, and this one is, in a different package, KV interface. Now you have put and get. And that also trickles down to the CLI. And it's getting even more interesting and funny if you're not setting the right, and that was my main lesson learned when I bumped into that, if you don't set the right environment variable, etcd controls, so the CLI tool that you can use to communicate and manipulate etcd, actually is in a different mode. So you might not be realizing that you're actually talking version 2, you think you're talking version 3. Next up is CockroachDB, which is what I would essentially say a key value store wrapped in a SQL interface. And the primary design goals are scalability, strong consistency, and survivability, which is somehow represented by the cockroach. And I like that logo a lot. And what happens is essentially that every node in the cluster can act as a SQL gateway and can map and execute SQL statements to these specific key value operations. And under the hood, they're using RocksDB for the persistency part, covering latency 0 and network is homogeneous. The overview architecture, as I mentioned, you have these nodes there with these RockDB stores, and the main challenge within RockDB is essentially you get in a SQL query and you need to map that to operations on key value stores, right? I found this talk by Ben Darnell, the CTO of Cockroach Labs, extremely interesting and insightful, where he goes on for, I think, an hour or so, explaining why they picked Go for, CockroachDB is certainly not the most trivial piece of software out there, compared with other things like C++, Java, and I think that were the 3 choices. So I encourage you to check that out. In this case, I picked a pull request, PR5512, which addresses 4 different issues. And that has a very nice title, RPC compute clock offsets in real time. Like, what's happening there? So it turns out, again, following all the trail down to a certain specific, the core of the patch, if you wish, led me to the package cockroach package RPC, the file clock offset go. And that has a new function, a method, verify clock offset, that you can apply to an object of type pointer remote clock monitoring. And if you look, so the overall description was like, yeah, I get it. And if you look on line 193, this is what you really want to read, right? Probably lots of tests to fix. Okay. And then I looked at the PR again and like back and forth, like, maybe that's too trigger happy. Maybe that's too sensitive. We're not sure. So they merged it, but they're still kind of discussing, is that maybe a bit too extreme? If you look through it, pretty normal stuff going on. You have a log there, iterating over. So again, reminder, what this does is it's essentially looking at the different offsets, and it returns nil if and only if more than half of the known offsets are healthy and an error otherwise. So yeah, it does what you would expect, logs it, goes over the offsets, and calculates that. And somewhere here, standard deviation 2 to 1, and down here, yeah. So that's essentially it. It doesn't look too complicated, but you can imagine that very often it's really hard to establish a relation between, you have some kind of issue on the one side, on the other side, what is the best way to go about that? And even if you have a fix, like in this case, the kind of like reminder to ourselves, we need to do more testing to really verify if the approach that we've taken here is really a valid one, the best one we can have for this case. Last but not least, Minio. Minio is essentially like, think of it like S3 that you can install everywhere, you can run everywhere. So it's an object storage server that is API compatible with S3. It's what I would call cloud native, container ready. You can store objects up to the size of 5 terabyte, and the storage API, which we're going to have a look at in a moment, essentially covers both local storage and network storage. They're using the good guys of Minio. They are actually present here, and I don't know, maybe Frank is around, so he can answer questions. Oh, over there. Can you stand up quickly, just so that people see? So that's Frank of Minio. If you have any further questions, I might not be able to answer. I will refer to him. Or come to his talk tomorrow, 11 a.m. in the community. 11 a.m.? Yeah, awesome. They're using erasure coding rather than replicating the data across nodes to protect it. And what I'm going to talk about in a moment really is the new gateway functionality, essentially proxy. Fallacies covered here are network is reliable and the cost is 0. Now, if we look at the design doc, and I believe that wonderful figure is not yet there, but will soon be. So there's a kind of preview Frank thankfully shared with me. Essentially has this object layer interface. It then has the FS objects and XL objects, XL for X large. FS objects just raw, and XL objects using erasure coding, and then depending if it's local or distributed, you would have POSIX and network storage implementing that. And then you would have the gateway layer, and I'm still a bit unsure what the arrow from object layer down to gateway layer is, because both of them are interfaces. But anyways, these 3 types here, Azure objects, S3 objects, and GZS objects implement the gateway layer interface. Now let's have a look at that. So in command gateway main.go, you have this gateway main, very unsurprisingly, doing a bit tricking with the context here. Okay. Then you handle the common arguments and the environment variables, fine. The main bits really, to me, is here. And this is the pattern you, in a sense, already have seen in the API server in Kubernetes. Set up a number of of handler functions and then apply those. So you register them if you wish here. So these are the ones I want to apply, and then use them slightly differently formulated than in the API server, but essentially the same idea. Then they're launching up this HTTP server, and then in line 354, they actually starting the HTTP server, listening on an error channel there, and also kudos to you, good on you in 358. Handling the SIG term. That's how it's supposed to be. And that's pretty much it. So in the end, you essentially just, depending on the input, say, like, am I talking to an Azure backend or Google or Amazon S3 backend, and then setting the respective mode. And that's pretty much it. So I find it a very clean and clear way how this gateway is implemented. Okay, so these were the case studies. I still have 13 minutes, which is great. This allows me some time for the Q&A part. First off, some general observations. Subjectively, going through all these issues and PRs until I found a few that I thought I could talk about and share, the top 3 things that I encountered there, I don't have really data that I can back it up. It was more like a hunch or a gut feeling, are timeouts, DNS, and resource exhaustion. So you might not have enough memory or whatever at the end of the day. GoDoc is awesome, and I think godoc.org, for example, provides the right incentives to really write good documentation, and I benefited a lot switching between looking at the source code and at GoDoc there. If you haven't read yet Peter Bergen's Go Best Practices 6 years, totally do that with an IAM operations, and it totally applies here. And one insight, and the projects that do that, I think, are also happy with it, make it possible to replicate the test suite and build pipeline locally so people can work offline. And also slightly controversial, a term I recently coined, container-assisted testing. Essentially the idea rather than mocking out something, you essentially pack everything in a container, and every time you run a unit test, launch a container. All right. Some further reading. If you're interested in the patterns part, check out Brendan Burns. He is currently at Microsoft, I believe. Designing Distributed Systems. Awesome book, and certainly useful. And he's using Kubernetes, so in a sense also Go, to explain the patterns. And with that, I'm at the conclusions part. Pretty good timing there. Essentially, number 1. Go is an absolutely great fit for teams, not only single teams, to build complex or evolving into complex distributed systems. This is my strong belief, and I hope that part of this talk supports that claim. Go scales, both in the human dimension and with respect to machines. And maybe for you initially, the machine part is more important. I personally think the human aspect is more important. We can discuss that. And looking through all these things, seeing certain patterns over and over again, I was wondering, maybe at some point in time we're gravitating towards a kind of common lib for distributed computing. And that would actually be awesome. I'm not sure if I'm in a position to suggest or write that, but I would certainly be interested in contributing to that. Having essentially a kind of library that you could just use to build your own distributed systems with Go. So take-home message, and here are all our 8 gophers again. And if that's the only thing you took away from this talk, then I call it a success. Please be aware of the 8 fallacies, and maybe you even now have an idea how to avoid them.